Welcome to our tutorial on Pydantic, where we'll learn how to make data validation simple and powerful. In this comprehensive tutorial, we're going to explore what Pydantic is and why it's become such an essential tool for Python developers. We'll cover everything from the base model foundation, automatic validation and type conversion, through to field constraints, custom validators, nested models for complex data structures, and various serialization methods. By the end of this tutorial, you'll have a solid understanding of how to use Pydantic effectively in your projects. Let's begin with a visual overview of how Pydantic works. Now let's look at the architecture overview. This diagram shows how Pydantic processes your data. As you can see in the image, data flows from various sources like JSON, dictionaries, or other formats into Pydantic models. The framework then performs automatic validation, type conversion, and applies any custom validators you've defined. If everything passes validation, you get a fully validated model instance. If there are any issues, you receive detailed error messages showing exactly what went wrong and where. Here's a comparison table that really highlights why Pydantic is superior to working with plain JSON. With JSON, you get no type validation. You have to manually convert types. There's limited IDE support, generic error messages, no data constraints, and any custom validation has to be done manually. In contrast, Pydantic gives us automatic type validation, automatic type conversion, full IDE autocomplete support, detailed error messages with exact locations, rich built-in constraints, and elegant decorator-based custom validation. This makes your code much more robust and developer-friendly. Let's start with our imports and check the Pydantic version. We're importing base model, which is the foundation of everything in Pydantic, along with field for adding constraints, field validator, and model validator for custom validation logic, validation error for handling errors, and some typing imports for better type hints. We'll also import datatime and JSON for our examples. Let me check what version of Pydantic we're running. Great, we're running Pydantic version 2.9.2, which is a recent version with all the latest features. Now let's dive into our first basic example to see how simple Pydantic makes data validation. This is the simplest possible Pydantic model where automatic validation happens right out of the box. Here we're defining our first user model that inherits from base model. Notice how we're using type hints to specify that name should be a string, age should be an integer, and email should be a string. When we create a user instance, Pydantic automatically validates that our data matches these types. We're also demonstrating automatic type conversion here. Notice how Bob's age is provided as the string 30, but Pydantic automatically converts it to an integer. This is incredibly useful when working with data from forms or APIs, where everything might come in as strings. Perfect. We successfully created our user Alice with all the correct types. You can see how we can access the attributes directly like user.name and user.age. And look at Bob's age. Even though we passed it as a string 30, Pydantic converted it to the integer 30. This automatic type conversion is one of Pydantic's most convenient features. Now let's see what happens when we try to create a user with invalid data. We're attempting to pass not a number as the age value, which obviously can't be converted to an integer. Pydantic will catch this and give us a detailed error message. Excellent. As expected, validation failed with a clear error message. Pydantic tells us exactly what went wrong. It couldn't parse the string as an integer. It shows us the exact field that had the error, which is age, and even provides the error type, which is int parsing. This level of detail makes debugging much easier compared to generic JSON parsing errors. Now let's explore field types and constraints, which give us powerful validation with minimal code. Here we're creating a more complex product model that demonstrates various field constraints. We're using constr for string constraints, setting minimum and maximum lengths. The price field uses decimal for precise monetary values with constraints that it must be greater than 0 and less than or equal to 1 million. We're using positive int to ensure quantity is always positive. We also have optional fields with defaults, like description, which can be none, discount, which defaults to 0 and must be between 0 and 1 representing a percentage, and tags, which defaults to an empty list. Let's create a valid product to see this in action. Great, our product was created successfully. The laptop has a price of $999.99, and as we can see, the description is none, and the default values for discount and tags were applied correctly. Now let's test various constraint violations to see how Pydantic handles different types of invalid data. We'll test an empty name which violates the minimum length, a negative price, a negative quantity, and an invalid discount greater than 1. Perfect. Each test case failed with a specific, helpful error message. Test 1 failed because the name must have at least 1 character. Test 2 failed because the price must be greater than 0. Test 3 failed because the quantity must be positive. And Test 4 failed because the discount can't be greater than 1. These constraint validations happen automatically without us writing any custom validation code. Let's look at another visualization showing the validation flow. This diagram illustrates how data moves through Pydantic's validation pipeline. Starting with raw input data, it goes through type checking, then constraint validation, then any custom validators you've defined, and finally either produces a validated model instance or raises a validation error with detailed information about what went wrong. Now let's explore custom validators, which allow us to add custom business logic using field and model validators. This account model demonstrates both field-level and model-level validators. For the username, we're validating that it's alphanumeric and at least 3 characters, then normalizing it to lowercase. The email validator checks for a valid format using a regular expression and also normalizes to lowercase. The password validator ensures it's at least 8 characters, contains at least 1 digit, and has at least 1 uppercase letter. We have 2 model validators that run after all field validation. One checks that the password and confirm password fields match, and another ensures the user is at least 13 years old. These model validators can access multiple fields to enforce cross-field constraints. Let's test creating a valid account. We're providing a username with mixed case and numbers, an email with mixed case, a secure password that meets all requirements, matching confirmation password, and an age over 13. Excellent. The account was created successfully, and notice how our validators normalize the data. The username John Doe 123 became John Doe 123 in lowercase, and the email was also converted to lowercase. This normalization ensures consistency in our data storage. Now let's test various validation failures to see our custom validators in action. We'll test a username that's too short, one that's not alphanumeric, an invalid email format, a weak password, mismatched passwords, and an age that's too young. Perfect. Each validation rule caught its specific error. The short username triggered our 3-character minimum rule. The hyphenated username failed the alphanumeric check. The invalid email format was caught by our regex pattern. The weak password failed because it was too short. The password mismatch was caught by our model validator, and the age restriction properly blocked the 10-year-old user. This shows how we can implement complex business rules elegantly. Let's look at how we can build nested models and complex structures. This diagram shows a model hierarchy where an order contains a customer, which has an address, and the order also contains multiple order items. Pydantic handles this nested validation seamlessly, validating the entire tree of objects. Here we're building a complex e-commerce order system with multiple nested models. We have an order status enum for order states. The address model validates addresses including a US zip code pattern. The customer model contains nested address objects for shipping and optionally billing. Order item represents products in the order with a computed subtotal property. The order model brings it all together with a customer, list of items, status, and timestamps. It has a computed total property that sums all item subtotals, and a model validator ensuring orders have at least 1 item. This demonstrates how Pydantic handles deeply nested structures elegantly. Now let's create a complex nested order from a dictionary, similar to what you might receive from a JSON API. We're providing order data with a nested customer object, which has a nested shipping address and multiple order items. Pydantic will validate this entire nested structure in one go. Fantastic! Pydantic successfully validated the entire nested structure. We can see the order was created with ID ORD 2024-1 for customer Alice Johnson, shipping to New York, USA, with processing status. The order contains 3 items: a laptop for $999.99, 2 mice at $29.99 each, totaling $59.98, and a keyboard for $79.99. The total comes to $1,139.96. All the nested validations passed, including the zip code pattern matching. Let's look at a practical example of API response validation, which is a common real-world use case for Pydantic. Here we're creating models for validating API responses. The API response model is a generic wrapper that ensures consistency. It can't be both successful and have an error, and failed responses must have an error message. The user response model validates specific user data from the API. We're simulating both successful and error API responses. The success response contains user data, while the error response contains an error message. When we receive a successful response with user data, we can parse it into our user response model for further validation and type safety. Perfect. Our API response validation is working correctly. The successful response is marked as success with data present. The error response shows success as false with the error message user not found. When we parse the user data from the successful response, we got a properly validated user object with username Alice_Wonder, email alice@wonderland.com, active status true, and member since January 15, 2024. This pattern is extremely useful for ensuring API responses match your expected structure. Now let's explore Pydantic serialization methods, which allow us to convert our models back to dictionaries, JSON, and parse them from various formats. Let's demonstrate all the key serialization methods. We'll create a simple order and then use model dump to convert it to a dictionary, showing that it returns a dict type with all the expected keys. We can use model dump with exclude to omit certain fields like timestamps. The model dump JSON method converts to a JSON string with proper formatting. We can use model validate to create a new instance from a dictionary, and model validate JSON to parse from a JSON string. These methods make it easy to work with APIs, databases, and file storage. Excellent! All our serialization methods work perfectly. Model dump created a dictionary with all the expected keys. When we excluded fields, created at was successfully removed. Model dump JSON produced a properly formatted JSON string. Model validate reconstructed the order from the dictionary with the same order ID. And model validate JSON successfully parsed the JSON string back into an order object with the correct customer name Bob Smith. These serialization methods are essential for API integration and data persistence. Let's explore some advanced Pydantic features that can make your models even more powerful. This advanced model demonstrates several powerful features. We're using config dict to configure model behavior, including automatic whitespace, stripping from strings, validation on attribute assignment, not just initialization, and forbidding extra fields that aren't defined in the model. We have a private attribute with private attr that won't be included in serialization. And we're using computed fields that are calculated on access, like display price, which formats the price with a $sign, and title length, which counts characters. Let's test these advanced features. Perfect. All our advanced features are working. The title laptop computer had its whitespace automatically stripped. The computed display price shows $999.99. The computed title length is 15 characters. When we assigned a new title with whitespace, it was also stripped automatically. In the serialized output, we can see the private internal ID is not included as expected, but the computed fields display price and title length are present. And when we tried to add an extra field, it was properly blocked with an extra forbidden error. These advanced features give you fine-grained control over model behavior. Let's wrap up with a comprehensive summary and best practices. We've covered all the key aspects of Pydantic. Base model is the foundation that everything inherits from. We get automatic validation, where types are validated and converted automatically. Rich constraints can be added using field and type annotations. Custom validators let us add business logic with field validator and model validator decorators. Nested models allow us to compose complex structures naturally. And validation error provides clear, detailed error information. The best practices include always using type hints for IDE support and clarity, validating early to catch errors at system boundaries, using custom validators for business logic, being explicit with optional for nullable fields, leveraging computed fields instead of storing derivable data. Pydantic is perfect for API validation, configuration management, data parsing, type-safe structures, and form validation. It's not ideal for simple scripts with trusted data, performance-critical tight loops, or when you just need a simple dictionary. Here's our final quick reference example that puts everything together. This quick reference model demonstrates all the key Pydantic features we've learned, including basic types, optional fields and defaults, various constraints, collections, nested models, field validators that transform data, and computed fields. This serves as a handy reference for the most common Pydantic patterns you'll use. Congratulations! You've successfully learned the fundamentals of Pydantic. You now understand how to create models, add validation, work with nested structures, and serialize data. The next steps are to try Pydantic with your own data, explore Pydantic settings for configuration management, check out FastAPI, which uses Pydantic extensively for API development, and read about advanced features like generic models. Pydantic will make your Python code more robust, maintainable, and developer-friendly. Happy coding!